ready? So good morning all of you. The summary of the last lecture, we have started this solid state physics and we just started this crystal structures. Am I right? Right. Now take a fresh page and put the heading crystal structures. Ready? What? Now first one, simple cubic. Let us discuss one by one. Simple cubic. So we have already given this notation. Simple cubic is represented by P, P for primitive. So what is this simple cubic? Now ready. So here we have, this is the simple cubic structure. So a lot of diagrams will be there. So have maintained patience, okay, and draw carefully. So for both teacher and student, it's a patience test. So that's it. This is the simple cubic. We have 8 corners. At each corner we have an atom, a lattice point and an atom like this. That's it. This is the simple cubic structure. For every crystal structure we need primitive vectors. I have already discussed you. Okay. So we need to find the primitive vectors. It's very simple. Here we can take this is A bar, and this is B bar, and this is C bar. Is that clear? So the translation vector, how you got all these points? By translation vector. T bar equal to N1 A bar plus N2 B bar plus N3 C bar, where N1, N2, N3 are the integers, A, B, C are primitive vectors. Be careful, primitive vectors. Okay. So what are these primitive vectors? A bar equal to, you know, it's a simple cubic, its length is A, here also A, here also A. Come on, say this is A x cap, B bar equal to A y cap, C bar equal to A z cap. These are the 3 primitive vectors which are giving you this structure, simple cubic. Now let us find a volume of primitive cell. Volume of primitive cell, because these are primitive vectors. If you want, you can write primitive vectors. Right. So the volume of a primitive cell. So everybody know what is the volume of these 3 vectors, A bar dot B bar cross C bar. If it is 3-dimensional vectors, then you have to take the determinant. Otherwise, you can do it directly. How much you will get? A cube. That is the volume of primitive cell. Shall I ask one thing? What is the volume of unit cell? Same. For simple cubic, it is same. So volume of unit cell. The volume of unit cell. How much? A cube. That's good. And let us start one by one. First one, number of lattice points per unit cell. Number of lattice points per unit cell. Wait ma, one by one. So how to get this number of lattice points per unit cell? I hope everybody know what is the sharing of this atom in the lattice structure. 1 by 8. That's why 1 by 8. How many are there? 8. That is equal to how much? 1. So the number of lattice points per unit cell equal to 1. That's it. Next, second one, coordination number. Coordination number. What is meant by coordination number? For example, if you consider that student, at a time with how many students she can coordinate? 4. So her coordination number is what? 4. That means coordination number means the first nearest neighbors. Don't say nearest neighbors. There will be many nearest neighbors. First nearest, second nearest, third nearest. Coordination number is always stands for the number of first nearest neighbors. Good. The number of first nearest neighbors. Right. Now listen. Let me take the diagram. So here I am taking a simple cubic structure. All of you please listen. So this is the simple cubic structure. Again one more I will take. Right. Now let me find. So what is the coordination number? That means I have to find the number of first nearest neighbors. Okay, I am taking this atom. For this I am going to find the coordination number. One on the right side, one on the left side. 1, 2. And the next other here, top 3. Okay, and here 4. Okay, next one more back. So this is 5. And next one more down. Are you observing? What is this? 6. So total coordination number is what? 6. So the number of first nearest neighbors, the coordination number for simple cubic, how much? 6. That's it. Next, third one. Radius. Radius of the atom. All these things you should remember. Not simply writing, you should remember also. That's why I am explaining how we got. At least if you forget, radius of the atom. How to get the radius of the atom. Again I am taking simple cubic structure. So primitive cell or unit cell, whatever it is. That's it. Now carefully see, here we have one atom, and here also, and here also, here also. For example, if you see carefully, you can take the atom like this, something like this. So so if you see carefully, if this is one of the atom, what is the radius? R, and this is also R. But this total side length is what? A. That's why R plus R equal to, so 2R equal to A and R equal to, so the radius of the atom in the simple cubic is A by 2. Next, fourth one. Listen. Packing fraction. Packing fraction. If you observe carefully, see this one. We are having 4 atoms, but 4 atoms are not completely occupying the side. There is some void space, there is some empty space. Like that, although you are having 8 atoms in that unit cell, all those 8 atoms won't occupy the complete space of the unit cell. In this classroom also, you are all atoms, let us suppose, and this is the classroom volume. Are you occupying the total volume of the classroom? There is some gap, there is some void space. So packing fraction means the volume occupied by the students. For example, one student V1, next student V2, next student V3. For example, all students individually same volume. Then N into V. Are you understanding? That is the volume occupied by students by total volume. It's a fraction. So that means, what is a packing fraction? The volume occupied by the atoms in the unit cell by volume of the unit cell. Say yes or no? 1 second. The packing fraction is defined as, 2 ways are there. Different authors will write a different way. Some people will take volume of the atoms occupied, volume of the atoms occupied by volume of primitive cell. That is one formula. Some people will write the denominator volume of unit cell. Then you must have a factor n in the numerator. That's why some textbooks will write n into volume of atoms occupied by volume of unit cell, because volume of primitive cell equal to volume of unit cell by number of atoms per unit cell. I don't know how many of you studied this in MSc. Okay. So the packing fraction, P I F A? F. Huh? F. P A? F. Packing fraction, F. Ready. So what is this packing fraction? Volume occupied by atoms by volume of primitive cell. Remember, volume of primitive cell is always equal to, are you listening? Volume of unit cell by number of atoms per unit cell. If you take this and substitute here, what you will get? N in the numerator. That's why don't be confused with both the formulae. Both are same. Some people will take volume of primitive cell. Some people will take volume of unit cell. If you write volume of unit cell, that is A cube in simple cubic, A cube in BCC, A cube in FCC. But volume of primitive cell is different for BCC and FCC. I hope you understand this. Okay. Yeah, first write down. There is no space. Yeah, 1 minute. Let me finish it. I think here is a space. 1 minute. F equal to, could you please tell me 1 minute, what is the volume of the atoms occupied? 4/3 pi r cube. Could you please tell me what is R? A by 2 whole cube by, now you please tell me, you want to take volume of primitive cell or unit cell? My advice, take primitive cell, because for every system we will find the volume of primitive cell. Here what is the volume of primitive cell? Of course unit cell is also same, because the number of lattice points is 1. That's why what is, how much it is? Still not understanding? Don't get tension. A cube gets cancelled and simplify and tell me what is the packing fraction. Pi by 6. Always remember, volume of primitive cell is minimum. That's why volume of primitive cell equal to volume of unit cell by n, where n is the number of lattice points per unit cell. Anything you can use, no issue. Just take the radius a by 2 and substitute and simplify. I think it is pi by 6. Pi by 6. Pi by 6 means 54%, amma. Please check. Later. If the gold is in simple cubic, will you buy it? If the gold is simple cubic, will you buy it? Why? Gold atoms only 54, remaining 46% empty space. So then what is the gold? What is the crystal structure of gold? What is the packing fraction of gold? Gold means RS, AU. So whenever you go to jewelry shop, please tell them there is a void space, I won't pay for that. I will pay for only packing fraction. You must remember each and everything. Crystal structures are very important. You will get one question sometimes. Yeah, already given in CSIR also. GATE definitely 100% sure question. CSIR also sometimes they are giving. Not sometimes. Crystal structure one question they are giving. Please see the relation between volume of primitive cell and volume of unit cell. Volume of primitive cell is less than or equal to volume of unit cell. That's why primitive cell volume equal to unit cell volume by number of atoms per unit cell, n. So the example for simple cubic, polonium, simple cubic structure. Polonium is also simple cubic, SC కాదు. 52 అమ్మా, it's a 52. You must remember each and everything. The volume is A cube and the number of lattice points per unit cell is 1. Coordination number, this is the 6, and that is the number of first nearest neighbors. Radius of the atom are equal to A by 2. While you are doing the problems, these are very important. And the packing fraction you must remember both pi by 6, 52%, 5 by 6, pi by 6 and 52%. Are you studying Wahab book? Please study just 1 hour study and leave it. Otherwise, before the exam if you open, you won't get interest and you lose the concentration. Ready? Please check whether pi by 6 is 52 or 54. I think 52. Check. Is it 52? Right, everybody. So what is the simple cubic structure? What are primitive vectors? A bar, Ax cap, B bar, B gaani bonda, Ay cap, C bar, Az cap. Next, volume of the primitive cell, A cube. Next, number of lattice points per unit cell in simple cubic, 1. Next one, coordination number, number of first nearest neighbors in simple cubic. Packing, radius of the atom in simple cubic. Packing fraction of simple cubic. Pi by 6 and 52%. Stop. BCC. All of you listen please. Now here we have, this is the BCC structure, body centered cubic. So cubic, that means unit cell is a cube. That's why volume of unit cell is A cube. Volume of unit cell no change. This is also cubic structure, that's why it is a cube. Now body center, here we have one body center and these atoms are the as usual corners, that's it. Now we have to write the primitive vectors first, okay. So now take the center as the body center, then one vector will be like this, one vector will be like this, and one vector will be like this. In this plane and this plane, is that clear? Then I hope you remember the translation vector T bar equal to N1 A bar plus N2 B bar plus N3 C bar. Now let me write the primitive vectors. Primitive. This A bar is defined as A by 2 because it is at body center. So there we will get A by 2. A by 2 into, remember, are you ready? A bar means along which axis? X axis. Generally we will take it as along X axis, generally A bar. So A bar, remember, along X axis. What are other two? Y and Y cap plus Z cap along which axis? Minus X axis. Now B bar, come on say, A by 2, other two, Z cap plus X cap minus Y cap. C bar. A by 2, X cap plus Y cap minus Z cap. That's good. B bar equal to A by 2, Y after Z, Z after X, X after Y. Next C bar equal to A by 2, Z after X, X after Y after, like that. Along X axis minus X cap, Y axis minus Y cap, Z axis minus Z cap. Other two are positive. Okay, Naina? Good. Now from this we have to find a volume of primitive cell first. Volume of a primitive cell. So the volume is given by A cube by 8 and the determinant minus 1, 1, 1, 1 minus 1, 1, 1, 1 minus 1. Anybody can say fast what is the answer here? X, 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 A. Forgot. Okay, do it. How much? Minus 1 into 1 minus 1. Can you do it? Yeah, please find it. Wait a minute. Next, first one. Number of lattice points. There is a trick you forgot, I think. X, 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 A. Your X is 1, your A is, X is minus 1, A is 1. Okay. Anta? 2. Number of lattice points per, can you do it now? Number of lattice points per unit cell. 1 minute. Ready. Amma, you know that this is sharing is what? 1 by 8. Like that 8 are there, but in the middle 1 is there. That's why answer. That's good. Next, second one. Coordination number. No need to write every time, just coordination number. You know what is meant by coordination number? The number of first nearest knife. If you take the middle BCC point, body center point, so how many are surrounded by it? 8. That's why coordination number. Next, third one. Radius of the atom. Amma, listen. You must remember this, not a joke. Please listen carefully. Radius of the atom. Okay, so let me find the radius of the atom. I am taking a BCC structure. So this is the BCC structure. Carefully observe. Now since it is a BCC, we have to take a body diagonal. Body diagonal means this point and this corner. Am I right? Or this point and this corner. It's difficult to show that. That's why I have taken this. So is it clear? This is the body diagonal. Okay, right. So in the middle we have a lattice point, and here also one lattice point, and here also lattice point. Now see, I'm just taking this line. I hope you are observing. this is the face and this is the face diagonal. This is what? Body diagonal. And of course, if you observe carefully, here we are having a 90 degrees. So this is how much amma? A. Amma, this is the face diagonal. Face diagonal, how much amma? Root 2a. Now, I am just checking at the body diagonal. So at this point we have one atom in the body at the body center, one atom at the corner, one atom at the corner. Okay. So this is R, this is also R, and this is R, and this is also R. If you see, it's a right angle triangle. Just apply Pythagoras theorem. R plus R plus R plus R, 4R whole square equal to A square plus 2A square. Can you find the radius? Start. Next, packing fraction. Find the volume and find the radius and find the packing fraction. Primitive vectors you must remember, otherwise we can't get reciprocal lattice. Yes, what is the volume you got? A cube by 2. Everybody got A cube by 2? Here how much amma? 4. Don't simply by heart, try to understand how we got the radius. It's a Pythagoras theorem. 4r whole square equal to a square plus 2a square. How much you got? Radius equal to root 3 by 4 or 2r? 4. Root 3 by 4. Huh? Please do it. It's a 7th class problem. R plus R plus R. 4r whole square equal to a square plus 2a square. So this is r square equal to 3a square by 16. That implies the radius of the atom is root 3a by 4. You must remember, for doing problems, while you are doing the problem, you should remember this. Radius of the atom in BCC, root 3a by 4. Don't simply copy that Pythagoras theorem, do it yourself. Next, packing fraction. You are taking primitive unit cell volume, that's why you won't get n here. For example, if you take unit cell volume a cube here, then here you must write n. Here n is what? 2. This 2 stands for the number of lattice points per unit cell. Easy to remember. BCC, number of lattice points are 2. That's why volume of primitive cell is a cube by 2. So this is packing fraction. 4/3 pi, that radius root 3a by 4 whole cube by a cube by 2. I have taken primitive cell. Can you please tell me what is the answer here? Pi by entama? Root 3 pi by 8. So please check root 3 pi by 8. How much percentage? 64? 68. Okay. 50 to 68. Simple cubic 52, BCC 68%. But remember that root 3 pi by 8 also. So see the primitive vectors of BCC, that is a bar equal to a by 2 y cap plus z cap minus x cap, b bar equal to a by 2 z cap plus x cap minus y cap, c bar equal to a by 2 x cap plus y cap minus z cap. Then the volume of the primitive cell is a cube by 2. Easy amma, unit cell volume by number of lattice points per unit cell. Number of lattice points per unit cell BCC 2. Coordination number BCC. Radius of the atom is BCC. Packing fraction BCC. Please remember both root 3 pi by 8 and 68%. Next, ready. Third one. FCC. Okay, that is face centered. My example written: lithium, sodium, potassium. Example for BCC: lithium, sodium, potassium. Lithium, sodium, potassium. Ready. So here the face center. Just see the diagram, after that you can start. Okay, so here we have the face centered atoms apart from that simple cubic structure. This is the front side and this is the back side, and these are the atoms at the corners. Now we have to define the primitive vectors first. Okay, so we know the translation vector is n1 a bar plus n2 b bar plus n3 c bar. Let me write the primitive vectors. Primitive vectors. How to get these primitive vectors? Very simple, amma. Take the origin here. Take the origin here. Okay. Now if you see carefully, from this is the face center atom in one plane. This is the another face center atom in another plane, and this is the another face center atom in the another plane. Total 3 planes will be there, xy, yz, zx. That's why your primitive vectors a bar equal to, it's a face center, that's why a by 2, a by 2. This is along which cap? That is lies in yz plane. That's why, come on, I say. Clear? Now come on, b bar, come on, say. Try, if you try then only you will get it, don't by heart. If you take the origin here, then one atom face center, face center, face center. That's why this is a yz plane, zx plane, xy plane. Clear, ma? Good. After this, you know how to find the volume of primitive cell. Volume of a primitive cell. So that is a cube by 8 into, can you find this? Okay. Next one. Number of lattice points per unit cell. Ready. So 8 corner points are there. Sharing is 1 by 8 plus 6 face center atoms. 6 face center atoms are there. Sharing is so total how much? So now tell me. Here definitely volume of primitive cell equal to a cube by 4. Volume of unit cell by number of lattice points per unit cell. Good. Second one, coordination number. Coordination number. Anybody knows what is the coordination number? 12. Coordination number for FCC 12. Simple cubic 6. BCC 8. You are forgetting. BCC 8. FCC 12. You draw and check how it is 12. Not now. Next, third one. Ready? Radius. Radius of the atom in FCC. So since it is a FCC, I am taking face diagonal. Okay, that means ready. So I am taking one face. So I hope you know this is the face diagonal. Okay. So at this face center we have one atom, and at the corner one atom, at this corner one atom, at this corner one atom, right? So this is how much, amma? This is also, but this is the face diagonal. Oh? Okay, wait. So this is how much? An atom, and a face center another atom, and a corner another atom. Here radius r, 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 r. Okay, ma? Now this is the right angle triangle. Again Pythagoras theorem. 4r whole square equal to a square plus a square. Can you do it? After getting radius, find the packing fraction. Come on, do it. Be confident. Do it yourself. I think here you will get 74%, I think. Do it yourself, you will get confidence. Don't take it easy. Yes, I think here you got 4r whole square equal to a square plus a square, and r square is equal to 2a square by 16, and r equal to how much amma? A by 2 root 2. So the radius of the atom in FCC, don't forget, very important, a by 2 root 2. Okay, so this is the volume of atoms, that is 4/3 pi a by 2 root 2 whole cube divided by volume of a primitive cell a cube by 4. I think here you will get pi by 3 root 2. I think this is a 74%, please check. Ready? Let us take a table, okay, with some more information. Whatever we have done till now, let us take a tabular form. So this is the conventional unit cell, simple cubic, BCC and FCC. First one, volume of, Amma listen please, volume of unit cell. Volume of unit cell in all the cases it is a cube. Next one, number of lattice points or number of atoms. Number of atoms per unit cell. We are taking a tabular form with all the information whatever we got now. Simple cubic, number of atoms per unit cell. BCC, FCC. That's why volume of primitive cell. Volume of primitive cell. So that's why here the volume of a primitive cell equal to here. That's it. Next, the number of first nearest. The number of first nearest neighbors. In simple cubic, number of first nearest neighbors. BCC, FCC, 12. Now, distance of first nearest. That is the number of first nearest neighbors. Now we are finding the distance of the first nearest neighbors. Ready? So in simple cubic, 6 atoms are first nearest neighbors. The distance from the origin, how much? A na A by 2 A by 2 ela? చెప్పు ఏదో ఒకటి చెప్పు. ఇందాక డయాగ్రామ్లో చూడండి, in the see the diagram, what is the distance we have taken? A. అబ్బాయి A by 2 అంటే. Next, in BCC, wait. Now see the body diagonal. Please go through the body diagonal. Could you please tell me what is the body diagonal length? Right. Root 3A. Root 3A. The body diagonal length is root 3A. That corner side length is A. This face diagonal root 2A. Then the body diagonal hypotenuse A square plus root 2A whole square. Root 3A. Clear? Body diagonal length. Half of that. Body diagonal root 3A. Half of that root 3A by 2. That is the first nearest distance in the BCC. Next FCC. Go to face diagonal. Face diagonal length how much? Root 2. A. Sorry. A. So face diagonal length is root 2A by 2. How much? Clear? So please remember like that. First nearest neighbors, you know, 6, 8, 12, but the distances also sometimes it is required for set exams. So simple cubic A. BCC, body diagonal root 3A by 2. Next, face diagonal root 2A by 2. Next, number of, sometimes if you are writing a gate exam, they will ask this, number of second nearest. In simple cubic, how many number of second nearest? Just guess. In simple cubic. 8. Me bonda. Any guess? 12. The number of second nearest neighbors 12. The number of second nearest neighbors in BCC and FCC same 6. Same, both are same. For second nearest neighbors in BCC and FCC 6. But here it is 12. Next, distance root 2A. A. Okay. So, and the last and final, packing fraction. If you are writing a set exam or gate exam, definitely you will get one question from this table. Please remember. Packing fraction. I need in terms of pi also. You please write. Pi by here. Root 3 pi by 8. Here. Pi by 3 root 2. Come on, write down. 74%. I think this is a 68%, 52%. please remember, before the exam we will see and go, then many things will be there to see before the exam. Once you prepare, just revise before the exam, you will remember. There will be one book, Problems in Solid State Physics, S.O. Pillai. If it is available, try to download S.O. Pillai. Solid State Physics by S.O. Pillai book is also there, and Problems, a separate book is there. S.O. Pillai. And Tamil Nadu? Pillai. Not Tamil Nadu. Which state? Huh? Maybe? Maybe Kerala. Once please revise those things, values. Please practice on the rough page. I will ask now those values. Please close that window. Every day please close it because the camera some shade is coming here. Ready? Right, stop. My next concept, areal density. This is also very important question for your GATE exam. Okay, so listen carefully, please. So this is the next one, areal density. Areal density of what planes? 100 plane, 110 plane, and 111 planes. Of which structure? A simple cubic I am taking. So this is a very important question. Listen carefully. What is meant by areal density? I think the word indicating areal density, the number of atoms per area. Area of what? Area of the plane. Area. Okay, right, wait a minute. So area of 100 plane or area of 110 or area of 111. Now first let me write, areal density is defined as the number of atoms in the plane, not in the lattice. The number of atoms not in the unit cell, the number of atoms in the plane by area of the plane. 1 minute. First let me take one by one. Babu, listen Babu, please. First I am taking a 100 plane. This is the Miller indices notation. Maybe tomorrow you will get that what is the Miller indices and all these things. Just listen. Now I am taking a 100 plane in the simple cubic structure. Now if I assume this is a 000 origin, so definitely this is what? 100. If I take this is x-axis. That's why I can take this plane as 100. Say yes or no? Now here one atom, here one atom, here one atom, here one atom. In this plane, how many are there? Sure. Wait. So in this plane we have one atom here, one atom here. Oh, little bit big we have to take. And one more atom here and one more atom here. Listen please. Earlier also we have taken the similar way, if you remember. Now one more time I am asking, how many atoms are there in the plane? One. Good. Why? 4 are there, but sharing is what? 1 by 4. Why 1 by 4? Sir, earlier you said 1 by 8. Now you are saying 1 by 4. 1 by 8 is for unit cell. 1 by 4 is for plane. I hope you are observing. Wait a minute. I will tell a small technique. Are you listening? So this is my plane. In this plane I have 4 atoms. But what about the sharing? If you observe carefully, listen. This is the side. So here, could you please tell me what is the angle here? So one of the atom is occupying this place. How much angle it is occupying? Total angle is how much? Out of 360, how much angle it is taking? That's why sharing is 90 degrees by 360. How much? Well, simple. So that's why the areal density, next one you have to do, listen. Areal density equal to the number of atoms in the plane. How many are there? But sharing by area. Area A square. That's why areal density for 100 plane is given by 1 by A square, centimeter inverse square or meter inverse square, whatever it is. This is for 100 plane. Clear? Still not understanding? No problem. Second one I will explain. Third one at least do it yourself. Again I am taking simple cubic structure. Now I would like to take a 110 plane. I hope some of you know at least. This is the 110 plane. Okay, so this plane. Are you observing? Good. We don't have any atom here. We have only atom at the corners. So that's it. One atom here, one atom here, next one atom here, another atom here. Okay. In the middle we don't have anything because it's not a BCCM. It is what? Simple cubic. Now ready. First get the sharing. How many are there? 4 are there. But get the sharing. At the corner you have one atom. That means how much angle it is sharing? Come on, sharing 90 degrees by how much? Okay. So next one. You have to get the area. Ready? Area. This is A. This is A. So this is root 2 and this is also A. Then what is the area? A into root 2A square. Okay na? So finally areal density, definitely a gate question, please listen. Areal density equal to total how many? 4. Sharing how much? By area root 2A into A. That's why 1 by root 2A square. Decreased or increased? For 100 plane. 110 plane. Decreased or increased? This is the straight plane. That is inclined plane. Next, third one. Oh, straight plane's areal density is more than inclined plane. Let us see. Now triple one. Triple one means you have to take x, y, z axis, 1, 1, 1 unit. That's why this will be like this. Okay. Now, so at this corner we have one atom and one atom. In that triple one plane, how many atoms are there? First let us get the sharing. Ready? Sharing, careful. So sharing. What triangle it is? Equilateral triangle, how much angle? Super. By how much? Play it. Now, ready? Areal density. While you are doing, please do it yourself. Don't simply copy, please. Areal density. How many are there? Sharing by equilateral triangle area. Triangle area. Half into base into height. Slowly. Half is as usual. Base. A. Root 2. Right. Root 2A into height. Height of equilateral triangle is root 3 by 2 into base. Don't say root 3 by 2A. If A is the side, then height is root 3 by 2 into A. So that's why, come on, I say root 3 by 2 into, that's it, root 2, So 1 2 cancel, final answer root 3 a square by 2. Okay na? So that is root 3 a square by 2. This 2 and this 2 gets cancelled. 1 by 2 both are cancelled. Answer 1 by root 3 a square. Again decreased or increased? Oh, this is the point. Straight planes areal density. Straight planes areal density is more than inclined plane density. Okay? Take some time. Diagrams are there. Do it slowly, no hurry. But draw neatly. How much patience I am showing, double the patience you have to show. Any doubt, please ask. Sorry. Only this is the sharing we are getting for this plane. That is 1 by 6th part is coming into the plane. Here 1/4 part, here 1/6 part. If you find some more good points from the book, please write in your notebook. So, but read the book once, just one time read, note down the points, or at least underline in the book. Maybe you are studying from the PDF file. Huh? If possible, buy that book. Not so much cost, I think around 400, 500 something. 400 Indian low price edition, because it's useful for your interviews, or if you become a teacher, then also it is useful. Okay, while you are doing research also it is useful, because any research definitely you will study with some materials, no doubt about it. One zero zero plane 1 by a square, 110 plane 1 by root 2 a square, and 111 plane 1 by root 3 a square. Areal density, the number of atoms in the plane by area of the plane. Ready? Right, next one. HCP structure, hexagonal closed packed structure or packing structure, whatever it is. Ready? All of you stop. Hexagonal closed packed structure, HCP. So here we have to first draw the unit cell corresponding to the HCP structure. Now for this, please observe the diagram carefully. Please draw like this, then it is easy. Take a line like this. I hope you are observing. And next take dotted lines. Whatever the height you want, just you can take and close it. Take the dotted lines here, and after that a little bit down, here, little bit down. Take the same length here, okay, but here take solid lines. Like this, okay. Then after that, take this, It's gone. Array. I practiced a lot, but still not coming. Okay. Ayyo. Ago. Like this. One more time. Right. So this is the hexagonal closed HCP structure. Okay, that's it. 1 minute. I think you can draw better than me. Right. Okay, right. So here we have hexagon, and here also one hexagon is there. So at each face we have one atom. Okay, and here also at each corner we have one atom. At each corner we have one atom. So two hexagons, at each corner we have one atom, and the center of the hexagon also one atom. Center of the hexagon is also one atom, and in the middle, so like this, perpendicular to the plane, perpendicular to this, we have one more 3 atoms. I request you, this like this is the like this. Okay, so here 3 atoms, and here 6 corners 6 atoms, 6 corners 6 atoms, and the here center 1, and here also center 1. That's it. So now let us come to the primitive vectors. If you take, this is the origin, this is A bar, and this is B bar, and this is C bar. Okay, that's it. Now ready. Okay, as usual we have to write the primitive vectors first. Primitive vectors. So A bar equal to root 3 by 2A, root 3 by 2A x cap plus A by 2 y cap. What is A bar? Root 3 by 2A x cap plus A by 2 y cap. Please remember. B bar equal to just minus. Minus root 3 by 2A x cap plus A by 2 y cap. Next, C bar equal to simply C z cap. These are the primitive vectors. Okay, now good. I hope you know how to find the volume. I need not to explain. So I request you take the determinant or your wish, A bar dot B bar cross C bar. Anything you can find and tell me the answer later. Next, first one. The number of lattice points per unit cell. Are you listening? The number of lattice points per unit cell. Right. So here how many corners are there? 6 corners are there. Okay. Can you please tell me what is the sharing of this? This is shared by how many? 6. 1 by 6. Am I right? Say yes or no? Okay. 6 and shared by, that's it. But Like this, how many hexagons are there? 2. Okay na? Plus, in the middle we have 3. 3. This is equal to 2 plus yo plus, now this is shared by how many? 2. That's why 1 by 2. Like that, how many are there? That's good. So this is a 2, 5, 1. Total 6. So the number of lattice points per unit cell in HCP? 6. Next, the second one. Coordination number. Coordination number. Coordination number. Anybody knows what is the coordination number? 12. HCP coordination number? 12. Next, third one. Radius of the atom. Radius of the atom. Don't get tension. So here we have one atom, here one atom. This side length is A. That's why, come on, say R plus R equal to how much? That's why R equal to how much? Still not understanding? See this, here one atom, here one atom. Okay ma? So total A is equal to 2R, R equal to A by 2. Next, fourth one, packing fraction. Packing fraction. Okay. So I will explain packing fraction separately because I want to say some more thing. Please write, find the volume and tell me. Come on. You please draw diagram and show me. First hexagon, what is the problem? If you draw 2 proper hexagons, you won't get this shape. Both will be coincide. That's the problem. If coincide, you can't show these things now. Try. The best diagram will get prize money. Who will give? The worst diagram person. I think that is me only. Come on. There is a small point, that's why don't find packing fraction. First find the volume of that primitive cell. How much you got? Root 3. Well, oh, diagram. Come on, come on. Ankita, where is the diagram? Good. Anybody got the volume? Root 3 a square by 2. Oh, root 3 a square c by 2. Correct. Better to take the determinant for this element C. What you will do? You will use a slide, sir, if you become professor. You will draw. Let us see. Ready. So you got this volume of the primitive cell is a root 3 by 2 a square c. Amma, listen, there is a small point here. All of you please listen. Actually, volume of unit cell, Amma, this is also very important question. Volume of HCP unit cell, this total unit cell equal to 3 times. How many times? 3 times. So 3 into there is no space, volume of primitive cell. Volume of primitive cell. Whatever the primitive vectors you define, the volume we are getting something, but the volume of this unit cell, this is called unit cell ma. The volume of this unit cell equal to how many times, sir? 3 times. That's why, once again, volume of HCP unit cell. HCP unit cell equal to how many times? 3 times. 3 root 3 by 2 a squares. Now I am doing a packing fraction in a different formula. So packing fraction equal to, earlier I told you, n into volume of atoms by, if I take n here, I have to take volume of unit cell. I hope you understand. So that's why I am using this formula here. N already we got how much? 6 into volume of the atoms of 4/3 by R is a by 2 whole cube by volume of unit cell 3 root 3 by 2 a square c. Can you get it? in that packing fraction, you have to use the ratio of C by A. C by A ratio I have given. I hope you know. What is the C by A ratio for HCP? Root 8 by 3. I think tell me what you are getting, packing fraction. It should be same as FCC, 74%. Directly you won't get the answer, you have to use that C by A ratio, you have to use under root 8 by 3. And then simplify, you will get the packing fraction which is the same as FCC. Please remember, volume of HCP unit cell is 3 times the volume of primitive cell. While you are doing the problems, you must remember all these properties, mainly radius of the atoms you must remember, don't neglect. In simple cubic, radius of the atom is A by 2. In BCC, root 3 A by 4. Radius of the atom, root 3 A by, BCC radius, root 3 A by 4. So FCC radius A by 2 root 2. Answer F equal to how much, Nanna? Pi by 3 root 2. Same answer, Babu, 74%, same as FCC. But here C and A will be there, so you have to use this ratio. Then only you will get that answer. Right. So once again, please tell me what is the radius of simple cubic atom? Simple cubic atom, A by 2. BCC radius of the BCC atom, root 3 A by 4. Root 3 A by 4. Next, FCC radius of the atom, A by. Ready. Problem. Find the maximum radius of, find the maximum radius of, find the maximum radius of interstitial, that means in between, whatever it is coming called interstitial. Find the maximum radius of interstitial sphere that can just fit into, that can just fit into the void and empty space, the void at half comma half, at 1 by 2 comma 1 by 2 comma 1 by 2, between the body centered atoms, between the body centered atoms of a BCC structure, between, underline that, between, underline from that, between the body centered atoms of BCC structure. Ready, I will explain. So one more time, see that last line, between the body centered atoms of BCC. So we have to take the BCC structure, everyone. So here I am taking the BCC structure because the question is about BCC. 1 minute. This is a very important model for your GATE exam. Okay. So one more I will take. So since it is a BCC, you have one body center here and here also one body center here. If you observe carefully what is the question, there exists a void between the two atoms of body center. So this is the body center, we have one atom here, we have one atom here. So in between there exists a void space. Then for that we have to find the radius of this sphere. Is that clear? Now see, now I am taking one atom at body center and another atom at a body center. This is the body center atom of BCC. That's why this radius you know, how much? R. This radius is also R. We already know in case of BCC, what is the radius of the atom in BCC? Root 3a by 4. Now, I am going to consider the maximum possible sphere which is a fit into the void space. Now, this total, this is unknown. While you are drawing, little bit big one you can draw, and this is the unknown. That's why I am taking 2r. Any trouble, ma? I think simple common sense. If this is a simple cubic, for example, or BCC, here one more cube is here. This is the BCC, body center, and here is a body center. Could you please tell me what is the distance between this body center and this body center? Come on. Array, this is a by 2, how much? So that's why this total distance is how much? Over. So r plus 2r plus r equal to, that implies 2r plus 2r equal to, 1 second. Is it a BCC? For BCC, radius of the atom. What is A? A equal to, so that's it, 4r by root 3. What do you want? 2r. 2r equal to 4 by root 3 minus 2 into 2 cancel, r equal to 2 by root 3 minus 1 into r. This is in terms of radius of the atom. In the options, sometimes they will give the answer in terms of parameter. What is the parameter? A. Then you have to resubstitute r equal to root 3a by 4. Don't forget, what he is asking, you have to be little bit careful. Is that clear? Come on. Next one, you please do it and tell me the answer. The similar question, but next one, you please do it. He may ask the answer in terms of A or in terms of radius of the atom, R. I think most of the paper setters will set the paper with the parameter A, with parameter A. While you are drawing, you please take little bit yellow color sphere, little bit small one you take. Then 2r will become little bit big. After crystal structures, you won't feel you are studying a new subject. You feel that you are studying quantum mechanics only. Crystal structures are little bit different algebra. After that, it's a total quantum mechanics, free electron theory of metals, chronic Penny model, band theory of solids. Next problem. Ready? Find the over. Is it over? Find the maximum radius. Find the maximum radius of the sphere. That can just fit into just fit into the void at the body center, of FCC. It's not body center cubic, at body center of FCC. Underline that, FCC. So here your structure is FCC. So listen, just I will draw the diagram, after that you please do it. Now FCC structure I am taking. We need 2 consecutive or successive atoms in FCC. So this is the phase center. Everyone please listen, this is the another phase center. Okay. With this center we have one atom. With this center we have another atom. He is asking the maximum possible radius that can just fit into at body center of FCC. That's why at the body center I am taking a sphere. This sphere radius is unknown, that's why it is 2r. This radius r and this radius, that's good. So finally I hope you know face to face what is the length a. It is a FCC, that's why you please take r, radius of the FCC r equal to a by 2. Come and do it. After that we have sodium chloride and a diamond and all these things, but drawing the diagrams is a bit difficult. FCC. So you have to take 2 successive atoms in FCC. Earlier BCC, 2 successive atoms of BCC. Answer root 2 minus 1 into 4 r 0.414 r. Root 2 is 1.441. 0.41. This is r plus 2r plus r is also equal to a, but this is FCC. So that's why radius is a by 2 root 2. So a equal to 2 root 2 r. So finally 2r plus 2r equal to 2 root 2 r. So finally r equal to root 2 minus 1 into r. R root 2 minus 1 into that small r is nothing but a by 2 root 2. Anything you can take, either this or this. That's it. So I request you, with this we have completed up to FCP structure. Still it is there, NaCl is there, diamond is there, graphene is there, or graphite is there. So if I am able to draw I will explain, otherwise okay. So that's it, and please go through the textbook and please read once and leave it today itself. Just read once and leave it, and again we can revise while you are going for interviews or something like that. Okay, that's it. Calicut, thank you.